Howdy! Welcome to Inspire Mountain Academy. I'm Professor Curtis, your instructor for this course in Introductory Statistics. In less than 10 minutes, this video explains what Venn diagrams and tree diagrams are and how they're used when considering probability. Let's get started. First up, we got Venn diagrams. These are just visual representations of events within a sample space. So here we have an example of a Venn diagram. So the box represents our sample space, and here we have a circle that's labeled A. So A occurs within this space bounded by the circle here. B occurs in the sample space bounded by this circle here. You can see there's an area of overlap where A and B cross over. So this is an area where A and B occur at the same time, and we describe it with this A plus B designation here. So when you see an area of overlap, that means A and B are intersecting. They're said to intersect each other. And this is the reason why, when we were using the addition rule, why we had to subtract off that last term, because we want to avoid double counting. Because, see, when you include the probability of A, you're including everything in this circle here. And then when you add in the probability of B, you've got everything in this circle here. So now this area of intersection has been added twice, so we have to subtract that intersection area out so that we only count that space once, and we avoid the double counting. Now it could be that events A and B don't overlap. In that case, you get a Venn diagram that looks like this. And in this case, A and B are said to be disjoint. Okay, another term for this is mutually exclusive, because each of the circles is mutually excluding the other. So obviously there's no overlap here. So that means that the events that are disjoint, they can't occur at the same time. Now, if you think back to how we define complements of events, so they are by definition disjoint. Something can't be A and then not A at the same time. So there's not going to be any overlap there. And because there's no overlap, they're by definition disjoint. Let's take a look at some example events, and we'll have you explain whether or not they're actually disjoint or not. So remember, disjoint events don't occur at the same time. They're mutually exclusive. So let's look at some pairs of events, and I'm going to ask you if you think that they're disjoint or not. So first up, we've got randomly selecting a data CD from an assembly line that is free of defects, and randomly selecting a data CD from an assembly line that has a faulty memory sector. Are these two events disjoint? What say you? Well, I hope you said yes, they are disjoint. If you've got an assembly line that's free of defects, you're not going to pull something from that that has a defect. And a faulty memory sector is a defect. So yes, there's no overlap here between these two events. They cannot occur at the same time. Therefore, they are disjoint. Let's try this next pair here. So a voluntary survey subject reporting a favorite color of blue, and a voluntary survey subject reporting a favorite color of red. Are these two events disjoint? Well, I hope you said yes. So here it's like, if you got a favorite color, then you've only got one favorite. I know some people say that they've got more than one favorite, but in reality, when you consider the meaning of the word favorite, there's only one thing that you can have to be favorite. So, if it's not one, it's the other. So these two events are going to be disjoint. There's no overlap there. How about receiving a phone call from someone who hates all ice cream and receiving a phone call from someone who hates vanilla ice cream? Are these two events disjoint? Well, I hope you said no. These events are not disjoint because there's some overlap. If you hate all ice cream, then you're going to hate vanilla ice cream. So there's an area of overlap here, and because of that overlap, they could occur at the same time, and that means that these events are not disjoint. And hey, you know what? Ice cream? I mean, how can you hate ice cream, man? Seriously, it's like, if you hate ice cream, get off my phone, man, because I don't want to talk to you. It is ridiculous. I mean, I can understand some people not liking vanilla ice cream. I happen to like it. I think it's a great flavor, among other flavors, of course. But, you know, how can you hate ice cream? That's ridiculous, man. I don't want to talk to you. If you hate ice cream, I don't want to talk to you. How about this set? Randomly polling voters and finding one who opposes abortion. Randomly polling voters and finding one who allows abortion under limited circumstances. Are these events disjoint? Well, I hope here again you said no. So if someone opposes abortion, then that means they're just flat out against it. If someone allows abortion under limited circumstances, that means there's going to be other circumstances under which they oppose it. And so there's going to be some overlap there between the two events. Because there's an overlap, they could occur at the same time, and that means these events are not disjoint. So if we consider what we've learned about complements, and we can combine that with the Venn diagram to come up with some rules for complementary events. So here we have our sample space bounded by the box, and here we've got our circle that defines all the space where A occurs. So obviously everything outside that circle is going to be not A. And if you take these two parts and you add them together, you get the whole kit and caboodle, which is 1 or 100% of everything. So if we take this equation here and we actually rearrange it, so let's say I'm going to subtract the probability of not A from both sides, I end up with, or actually the probability of A from both sides, I end up with this little guy here. So the probability of not A is going to equal to 1 minus the probability of A. And I could switch that up. So, you know, I could come and get this equation here if I subtract the probability of not A from each side. So these three equations are really saying the same thing. We can get, you know, if we know everything, which is 1, and then we know one of these two, we can get the other one just subtracting from 1, because both of these together have to add up to everything. Let's talk for a moment about tree diagrams before we wrap this up. So tree diagrams are what you see here. It's just a group of line segments that emanate from a starting point, and they end up showing the possible outcomes for a procedure. And these can be very helpful for figuring out what your sample space is and how many items you have in your sample space. But it's really only that helpful if the sample size is kind of small. If your sample space gets really huge, then, you know, these trees can get really big. So it's only useful if the number of possibilities you're looking at are pretty limited. Note we can predict the total number of outcomes in the sample space if we know how many options are available. So here we've got a tree diagram where we're showing a coin toss. So in the first toss, we can get a head or a tail. Then we toss it again, so we can get a head or a tail after each of those. In a third toss, we can get a head or a tail after each of those. And so we just get the outcome here. So this first one is the head, the head, the head. So that's the first outcome. Then we got head, head, tail. That's the second outcome. And we just go down the list and we find that we actually have 8 outcomes total. So if we start with the first 2, and then we've got 2 and 2, and then we've got 2 and 2 and 2 and 2. So that leads us to have 8 outcomes in our sample space. So that's the size of our sample space there. Notice we can get that same number 8 if we just do a little calculation here. So there's 2 choices each time we toss the coin, and there's 3 tosses, so there's 2 times 2 times 2, 2 choices in each of 3 tosses. Multiply that together, that gives us our sample size. So we don't have to draw the tree diagram to get the size of the sample space. We can just run this little quick calculation. But anywho, that's your tree diagram. And that brings us to the end of this mini lecture. I hope you found it helpful. You know, you can find other mini lectures for this and other courses at aspireboundacademy.com. Thanks for watching. I'll see you in the next video.